Hello everyone and welcome to Vibrations in Acoustics. Today we're going to work with a spring mass system that has a forcing function applied to it. You can go ahead and read the problem and see what all the conditions are for the forcing function. I'm actually going to work this problem two different ways in two separate videos. So if this way is not one that's familiar to you or you want to see a different kind of method, you can go ahead and look at the method 2 video of this problem. Okay, so going the quickest route with this problem is to really just jump into a set of equations, and hopefully your instructor has introduced you to the equations that I'll use in this problem, and you'll be able to basically plug and chug for most of this problem. Excuse me. So what we're looking at right here is based on the information that we have right now. We can look at this f of t, which is equal to 100 sine of 6t. Right here, you already have an f naught and excuse me, and omega equal to 6. We also have k given to us. We also have the mass given to us. So from there, it's actually pretty simple. We can go ahead and immediately find omega n that we'll be using for this problem. And omega n is equal to the square root of k over m for any vibratory system. And if you solve this out, 4,000 and m equal to 100, stick those in there, you should get 6.324 radians per second as omega n. And then we know that omega is equal to 6 rads per second. Okay, so now, moving on from there, we've gotten all the basic information that we can get from this based on what the initial values. So now we need to look at the system, and what kind of a system do we have? Well, we have a spring and we have a mass. You can solve some of the forces and get an equation of motion from it, but when you see this kind of system, you should be able to immediately jump to the equation. Here, let me show you that system. mx double dot plus kx is equal to the forcing function, which in this case is 100 sine of 6t. So basically you have the inertia plus the force of the spring is equal to whatever the forcing function is applying to this. Pretty quick and easy. Okay, now looking at that, going a little bit further, you should also be able to see that since it is an oscillatory system of just a spring and a mass, you can go to the equation a sine of omega nt plus phi plus x sine of omega t. And this is the homogeneous solution. Hopefully you've been introduced to this. This is equal to x of t. This is the homogeneous solution, part of the solution, and this is the particular part of the solution. And you can derive this straight out from this problem if you don't remember this equation, and I'll do that in method 2. But hopefully you can keep this on an equation sheet and just crank right through it. Okay. So, now that we've established the basic equations here, the things that we care about, we need to go on and figure out how the system is going to react when there is no forcing function. So you basically take this equation right here and solve it out without the forcing function. So basically mx double dot plus kx equal to 0. So basically no forcing function. And if you do this, what you'll end up with is moving mx double dot over to the other side. Mx double dot is this right here, basically the normal force in this direction. And how do you get this force in this direction? Well, this is going to equal mg sine of phi. So mass times gravity times sine of this, which is the mass forcing down right here, the angle phi, which is the inclined angle of this, and then just going ahead and taking the sine of that angle. And you get the force that's operating this direction. And since there's no friction in this system, we don't care about the normal force acting downward right here. So we can neglect that. So basically doing the sum of the forces here without the forcing function, you get mx plus kx is equal to 0, which then can be converted to ax naught, which is the original displacement of the system, basically, the initial condition. If you just let this mass go and you just let it sit there, if you let this mass fall down the hill as far as it can with the spring there and without applying any external forces, F naught, to it, then kx is equal to mg sine of phi, just a sum of the forces calculation. And then solving for x naught, which is equal to mg sine of theta all over k. And subbing in these values, we have a mass of 100, 9.81, times sine of the angle 20 degrees, all over 4,000, which is k. And this will yield 0.084 meters. This value is how far this block slips down the hill just sitting there. Basically, you hook up the spring in your block and you let go of the block, and the spring extends a little bit and the block slides down 8 centimeters basically. So that's an initial condition that in order to get the full x displacement from just a basic system where absolutely nothing is extended, that's how far it's extended, added on to whatever the forcing function will cause now. And you need this to get a complete solution. Okay, so now we know that x dot naught is equal to 0 because the derivative of a constant here is just going to be 0. So there are our initial conditions. So moving on with this, we have, if we're looking up at this equation now, we have omega n, we need phi x a, and we have omega. So in order to get this complete equation, it's going to be xh plus xp, and then actually plus this right here. And in method 2, I'll show how that whole derivation works because it's a longer method, but hopefully you'll be able to become familiar enough with this stuff that it won't be that big of a deal. So now, phi is equal to a tan 2 of x naught by x naught dot all over omega n minus omega over omega n f naught all over k of 1 over 1 minus omega over omega n squared. Okay, and if you haven't seen the omega over omega n before, that is just r. R is equal to omega over omega n. So if your professor's introduced it in that way, that's where this fraction comes from in this equation. Okay, so that's phi, and then a is equal to the square root of x naught squared plus x naught dot all over omega n minus omega, oops, let me let you see that, omega over omega n f naught over k of 1 over 1 minus omega over omega n squared. And as you can see, these are the same values being used in both of these. So x naught is stuck in here, this is stuck in here, this is actually squared, sorry, because this is Pythagoras' theorem basically. And if you watch one of my earlier videos, I explained this a couple of times. And then these are all multiplied, these are all multiplied. Okay, and if you crank through that, x, you can also define x itself up here in this equation. We've got phi and a, now we need x. X is equal to f naught all over k minus m omega squared. Now we don't have f naught, this is just f, I apologize, not f naught. This is the f, which is the force, which is equal to f naught over k all over 1 minus omega over omega n squared. Okay, now the thing about this is, oh no, this is f naught, I apologize. But then you divide by k, divide through here, and then m over k becomes omega over k squared, and you can just go from here. So if you look at this, if omega n is equal to the square root of k over m, if you take m and you divide it by k, then you've got 1 over omega n, which is omega over omega n then, squared, basically. So k over m is equal to omega n squared, and you can see how you get that. I don't want to completely show that out. Okay, so now solving all of these out, a will equal square root of 0.084 squared plus 0 minus 6 over 6.324 times 100 all over 4,000 of 1 all over 1 minus 6 over 6.324, square that, take that, close that last parenthesis, Square that piece, and you should get A is equal to 0.2516. Phi is equal to tangent inverse, or atan2 if you're using MATLAB, 0.084 all over minus 6 all over omega n. I'm not going to show all this out because you guys know what the values are. 4,000 all over 1 minus 6 all over 6.324 squared. All over that. And this should give you, this will give you a degree measurement. If you do this calculation in degrees, you should get negative 19.46 degrees. But if you do it in radians, you can do a conversion, 180, or calculate this in radians. Or if you do degrees, do a conversion, and this should give you negative 0.3396 radians, which is the value there. And we got the A right here, that right there. So now let me move this up a little bit. And now do the calculation for x. X is equal to 100 over 4,000, because f naught is the forcing function right here. The value of the forcing function, this 100 is f naught. So all over 1 minus 0.9488 squared, because I did this calculation a little bit earlier, which is equal to 0.25. So we have all the values that we need now to solve this equation. So if we're looking at this equation right up here, we also have to remember that x naught is equal to 0.084. This is important because it's not explicitly stated in this equation, but if you're trying to find the total response of a system with respect to standard x and not like x tilde or something, then you have to include the displacement caused by just letting the system sit, the static displacement basically. So then this will all yield x of t, subbing in the values that we got earlier, 0.2516, which is equal to A, sine of omega n, 6.324 t, minus the phi that we got, which is negative 0.3396, plus 0.25, which is x, sine of omega t, which is 6t. And then you add on the last little bit, which is the x static, or x naught, right up here, 0.084 meters. And that is your total response for this system. If you don't want to include this 0.084 and just say the response of the system after like setting or something, then you have to say x tilde of t is equal to this piece right here, and just not include that initial displacement basically. And that's how you find the total response. That's one way of doing it. That is actually a quick problem if you don't have to go through show all the steps and stuff. Now I'm actually going to go through and derive it, so if you want to watch method 2, you can get some of the greater background of how this problem works.